So we are now looking at something called Big O notation. This is a way that mathematicians and computer scientists describe basically how fast functions grow. If you're a mathematician, you want to be concerned with the bigger terms, not concerned with the lower order terms. Something you might see in Calculus 3 when you're doing Taylor series from a certain point of view. Computer scientists use it when they want to describe things about algorithms. So I'm going to give you this definition here in terms of functions in just a second. But first, I want to show you a little bit of motivation from the computer science perspective. So suppose you have two different algorithms. We're going to call them algorithm 1 and algorithm 2. And they both accomplish the same task. So this could be sorting or a search algorithm or just any type of algorithm you want. But two different algorithms both do the same thing, but they do it in different ways. So let's suppose that this first algorithm, which we call algorithm 1, if you input n operations, it will run in n plus 1. Excuse me, if you input n inputs, this algorithm runs in n plus 100 operations. That's how many, additions, subtractions, searches, assignments, anything you want to consider an operation, it will take it n plus 1 operations to run if you give it n inputs. And I have another one called algorithm 2, and it will run in n squared inputs. Excuse me, n squared operations for n inputs. So the question is, which of these is the more efficient algorithm? Well, if you only have one single input, then algorithm 1 for one input will take 101 operations. Algorithm 2, if you input one input, n equals 1, it will run in one operation. So in this case, algorithm 2 runs faster because there's fewer operations. If we go up one order of magnitude to n equals 10, well, algorithm 1 will run in 110 operations. Algorithm 2 runs in 100 operations. So algorithm 2 is still slightly more efficient, but computers are so fast these days that 10 operations really isn't anything. What if we go up to n equals 100, go up another order of magnitude? Well, in this case, algorithm 1 will run in 200 operations, but algorithm 2, it will take it 10,000 operations to finish. And as n, gets larger and larger and larger, algorithm 1 will always run so much faster. Okay, 100 operations on a computer, that's nothing. So there's really no difference when n equals 1 or n equals 10. But when we get to n equals 100, when you start dealing with bigger and bigger data sets, the difference in the number of operations is dramatic. Algorithm 1 will run much faster. I mean, when n equals 1,000, if n is equal to 1,000, we'll go up another order of magnitude. Then algorithm 1 will run in 1,100 operations, but algorithm 2, it takes it 1,000,000 operations to run. So, clearly algorithm 1 in general, algorithm 1 is going to be a much better algorithm. And when we do Big O, what we concern with is the worst case scenario. That is, what happens when we have lots and lots of operations? Which algorithm is ultimately going to be better? So I want you to keep that in mind when you're thinking about this Big O stuff, because what we care about is what happens in the long run. Okay, let's go back to the notes and look at this technical definition of what Big O says. And this is given to you in terms of functions. And then we'll translate that into algorithms just by letting our functions be on natural numbers or positive integers rather than the real numbers. So I'll start out with two functions, f and g. They're functions from the set of integers to the set of real numbers. So our input here is going to be integers. That's like the number of inputs you would have. And give it like that. we say that f of x is big O of g of x, and that's how it's written. Now, as an aside, if you're looking at other things online, you may see this written sometimes like this. F of x is equal to big O of g of x. I don't like that notation personally because it's kind of an abuse. So we're always just going to say f of x is big O of g of x. But just be aware that you may see this, what I consider bad notation, if you look in other things. So what that means is there exist two positive integers, a and n, and this pair, this a and n pair, these are called witnesses. If you can find positive integers a and n such that this inequality holds true, the absolute value of f of x is less than or equal to a times the absolute value of g of x when x is bigger than n. So in other words, we can go far enough over on the x-axis so that f of x is less than or equal to a constant times g of x. So this little paragraph right here says, that means if we want to determine if a function f of x is big O of g of x, we have to identify, we have to find an a and an n. And that's all we have to do, find an a and an n that makes that inequality true. So here's an example given to you using 3x cubed plus 18x. This is big O of x cubed. So before I go through what can be called an analysis type argument, let me show this to you graphically so you can see kind of what I'm talking about. So let's look at GeoGebra. And what I'm going to do is I'm going to graph those two functions. I'm going to graph, the first one was 3x cubed plus 18x. There's the graph of this function. I'm going to change my view in just a second. Actually, I'm going to do that now. We can't really see what's going on. This just looks like a line here. But if I zoom out and stretch this way, let me stretch this down, and we can see that there is actually some curviness going on to this function, okay? 3x cubed plus 18x. I'm also going to graph x cubed. So the claim, okay? The claim, recall, is that 3x cubed plus 18x is big O of g of x. So what should that mean? If that's true, what should that mean? Well, that should mean that if I go far enough over, along the x-axis, I should be able to get a constant times x cubed bigger than this function right here. That is, I should be able to get the blue function over on top of this reddish function if I go far enough over, okay? So from here, it doesn't look like it's going to work, just looking at what we have. So why don't I try putting some constants in here? So I'm going to put the constant 21x, and then look what happened. There's this point where these functions cross each other at x equals 1, and f of x is about 21 maybe. And if I zoom out, let me make my x-axis really, really long so we can see really far over. And I'm going to shorten my y-axis. So look at that. After x equals 1, the blue function is always on top. Okay? And that's all that it means to be big O, that there is eventually going to be a point on the x-axis where the red function is smaller than some constant times this blue function. So let me write this out. So what we're saying is that g of x, which is our, excuse me, I started that out wrong. We're saying that f of x is big O of g of x. That is, we're saying that 3x cubed plus 18x is big O of x squared. By definition, that means there exist positive integers a and n, so that if x is bigger than n, then the absolute value of 3x cubed plus 18x is less than or equal to a times the absolute value of x cubed. And I said squared up here, but of course that's supposed to be cubed. Now from the graph, we can see where that happens, okay? If a is equal to 21, there's my a, then the n, where the change happens, is equal to 1. So I'm saying if x is bigger than 1, then, and since these functions are positive, bigger than 1, I don't need the absolute value stuff. I can just say then 3x cubed plus 18x is less than or equal to 21x cubed. And that's exactly what this is saying. This is my I'll say red orange. We'll say orange. This is the orange graph. And this is the blue graph. As long as x is bigger than 1, then the orange graph is smaller than the blue graph. And this never, ever, ever, ever changes. Right? I can keep dragging my x-axis over and over and over to have bigger and bigger values of x and bigger values of y. And this never, ever changes. And this is all that big O means for functions, that I can go eventually far enough along the x-axis so that the f function is smaller than a constant times this bluish colored function. Okay, this is what it means for functions. Now, this is how you do it with a graph. I want to show you how you can do it analytically in a couple cases. So let's look again at, well, let me just get something blank that I can write on. So I want to show analytically, that is by drawing, without drawing the graphs, I want to show that 3x cubed plus 18x is big O of x cubed. Now, there's another video that I want you to watch that gives you an example with polynomials that discusses why, if you have polynomials, you can use x equals 1, something special happens. Okay, at x equals 1, something special happens. And in fact, I don't want to say x equals 1. I want to say that when x is bigger than 1, then I'm going to have that 3x cubed. So nothing's going to change with this term. So I look at these term by term. And so no change here. But 8x is going to be less than or equal to 18x cubed. So I look at the second term. And what I'm doing is I'm replacing everything in there with something times x cubed, because that's going to let me say that 3x cubed plus 18x is less than or equal to 3x cubed plus 18x cubed. And that right-hand side, that's equal to 21x cubed. So that gave me that 3x cubed plus 18x is less than or equal to 21x cubed. And I'm finished. I'm finished because I found my witnesses. I said if x is bigger than 1, which tells me that n is equal to 1, I get that 3x cubed plus 18x less than or equal to 21x cubed, which says that my a is equal to 21. And this is all that we need to say that something is big O, because look at the definition again. I just have to find an A and an N that makes this true. And that's exactly what I did. Okay. Now, this example shows that we can use other numbers. I don't have to use n equals 1. I can use n equals 5, and then I'll get a different A. So read through this example too, and this is graphed with GeoGebra or Desmos. And that's basically what Big O is built on. Okay. The rest of this is looking at some important facts and ordering functions. So please read through the notes and watch all those example videos. And if you have any questions, as always, let me know and I will answer them for you. And I'll talk to you next time.